This lecture is a small digression from our trip through time of life and the earth and what's happening through time to talk about how we do mapping and also a little bit on the local geology. This is a good place to put it because our local geology is largely early Paleozoic, the previous lecture, Ordovician, and so that's what would be on the local geologic maps. And so here's where we're going to do this stuff. So, geologic maps. Remember William Smith? He was the one that sort of created or gave us the knowledge of how to use fossils to tell time. He's actually more known for producing the very first surface geology map. And so what you're looking at there is the cover of a book, and the title says it all. This is the map that changed the world. Because he created this way of mapping geology, we have a way to find resources on planet Earth, whatever it is, oil, gas, precious gems, metals, simple things like gravel and sand. This has returned many billions, and I would say even trillions of dollars of return on investment. Because this works, we know how to find resources. So look at William Smith's first map. There it is. It is a map of England, Wales, and a little bit of Scotland. And what he did, wherever he went, remember he was digging canals and places to construct things. He would look at the rocks, he would collect the fossils, we already know that, and he would mark where he found them. But then he would describe the rocks that he found at the surface. And for rocks that had different types, so let's say sandstones containing trilobites, then he would find a few miles away limestones containing different trilobites and maybe some crinoids. He would color them in on the map. And so these weird color patterns you see on the map are showing different rock types of different ages. We still do this today. So here's a map of West Virginia, and you see here the different colors across it. The little black outlines are the counties of West Virginia. It's a weird shaped state, isn't it? But then look at the patterns of colors, and it shows the different age rocks that are found here. If, for instance, you know that the Cambrian rocks have, let's say, pick something weird, they have molybdenum in them that you can mine and sell, and this molybdenum then is part of what we need to build our cell phones. Cell phones contain over 40 different minerals in them, and they come from mines in different places. Let's say you know that these Cambrian rocks in other states have it. Where are you going to find it in West Virginia? This tells you right away exactly what counties you need to worry about, these extreme east ones over here. The next few slides are just a bunch of pictures of other places, just to show you that at many, many levels, there are places or entities called geological surveys. Every state has them, the federal government has them, most countries have them. Some smaller entities, some counties do this, some cities do geologic mapping, and it's important to show because of the rock types that are there. It's not all about just getting resources too. Certain rock types here are more susceptible to radioactive minerals, and so the basements in those areas might be filled with radon. Other rock types might be more susceptible to landslides. And so mapping these things, mapping rocks tells you both where you're going to make money by getting resources, but also where you're going to potentially lose money and life by hazards. So there's the state of Texas, and Texas by any measure is if it were an independent country, it would be one of the wealthiest countries in the planet because of its geological resources. Here's a different state, Nevada, different colors, everything, and then different patterns. So instead of the long, sweeping, stripy layers, you see this sort of zebra-type pattern. These also indicate geology. And so Nevada looks like this because it has a divergent boundary sort of opening up underneath it, spreading and breaking the rocks across here. Again, all of these different colors, never forget the different colors represent different rocks containing different fossils. Here's a bigger map. Let's get rid of these things. This is the geological map of Western Europe. And here, multiple entities. Think of all the different countries of Europe, but also the European Union, all the different languages involved here, but this transcends all of that. The geology of all of these things are independent of the political boundaries. So if, for instance, you see in this dark purple pattern, let's say we know in England that that dark purple pattern contains coal of a very high purity, low sulfur content. You can burn it with very little environmental effect. If you find the same age rocks in these other places, let's say Spain, France, Belgium, Poland, Russia, and the far, you know you stand a much better chance of getting that same valuable resource there. Here's another one. Let's get rid of these things. They shouldn't be there. This is a map of the Middle East, Saudi Arabia mostly, and you know that the Middle East is one of our other huge sources of petroleum, oil, and natural gas in the world. And one of the units that's particularly important in Saudi Arabia is this blue one. Now this is the surface geology. But of course when you drill for oil, you're drilling in the subsurface. And notice these little marks over here. These look like little capital T's. You have a cross and then a pointy end sticking off this way. These are important. These are what we call strike and dip markers. The pointed end, the one that's sort of coming down from the top of the T, points to the direction that these rocks that are exposed at the surface are plunging into the subsurface. These rocks are no longer flat, like Steno said they had to be originally. They're bent, they're folded, they're going into the subsurface. In the subsurface, this unit is drilled and has returned, again, several $1 trillion worth of value to the country of Saudi Arabia and fueled economic and cultural development worldwide. Mapping this, including knowing how much this is dipping, has helped us sort of discover these rocks and make them available to everybody. Here's just a smaller map that we can look at. This is a map of Montgomery County, Maryland. So Washington, D.C. is right down here in this sort of little polygon you see here, but there's Montgomery County, Maryland, and you see at this smaller scale, they have mapped the different rock types here. And you can map it at any scale. You can map it as, you know, the geologic map of the Bethesda city limits. Mapping is done at many different scales. And when we have all these different patterns, you might ask, well, why are there these weird stripy patterns here? And yet they look different when we're looking at Saudi Arabia or Europe in general. Or why does Nevada look vastly different than Texas? Think about it. All these places are in different situations tectonically. Tectonics bends and breaks rocks, and it creates what we call geologic structures, which we need to learn about now. So geologic structures, you see in this picture right here, the green and brown, that would be the surface of the land, you know, sort of low valleys, higher mountains, and you can see this slice into the earth shows that the rocks, which were originally flat, have been bent. They've been folded. This is called folding. And we have two types of folds you need to worry about. The first are what we call anticlines. This is where they are upward bending. The limbs are pointing downward, and you create these huge, notice it's sort of in the shape of an A with the point at the top this way. And here's the cartoon. Here's a picture of a mountainside in Maryland. I believe it's Maryland. And you see this anticline. These rocks have been bent or folded this way. If you can fold rocks up, you can also fold them down. So imagine that this is a carpet and you've kind of pushed on the edge of it. You're going to create big upward folds, anticlines, and then downward folds, synclines. And here, this is a road cut. You can see the road barrier on the side here, and then you see where they've cut through the rocks and they're making a syncline. Syncline begins with an S. These look like smiley faces, so anticlines, big A's, synclines, smiley faces. They're not always perfect U shapes like this. Here is a picture of a syncline, a fold, and notice the rocks come in from the right here, they dip down, then they make a sharp increase up like that. That's still a syncline because it's a downward fold. Off the camera to the left and the right would be anticlines. Well, how do we measure them? We have two things we do. We call it the dip, and that's the angle that these beds are folded, and then the strike, which is the perpendicular to it. So here's a fold. I hope you can see that this is an anticline because of its big shape. And notice on the left side of the anticline, these beds are dipping down into the earth, and they're dipping down at a particular angle. Look at the right side of the anticline. They are dipping down here, but they're dipping far more steeply. Now, if you are interested in let's say that this brownish tannish rock that you see in the side of this mountain here and exposed here, let's say it contains particular grains of a garnet that you need to mine or you need to get to make the toughest sandpaper or industrial grinding surfaces. You know that to the left, let's call that to the west, this unit dips down at a certain level, and that if you needed to mine for it, here you would need to shaft the mine or dig down, let's say 100 feet. This same unit to the east, to the right side here, dips down at much steeper angle, and if you were going to have to make a mine for this over here, notice to reach that same rock, you're going to have to dig down many hundreds of feet. This side's cheaper. This side is more expensive. But what if this is a boundary between two states? Then the environment, that the economy of this state, which would get tax dollars from getting this, would benefit more than this state, because any mining company, any company would say, I'm going to have to spend less money to get it here, I'll do it here. It's that simple. The strike is the other direction. It's the compass direction of the way the rocks are trending. All you have to remember is that it is perpendicular to the dip. If you go to the rocks and you see where they're dipping, and I'll give you a clue in just a second how to do that, then you can literally lay a compass or your cell phone even on there and do the strike. And this tells you that, okay, this rock unit, it's going to be found, if these were west and east before, it's going to be found to the north and south in what general direction? More to the west, more to the east, whatever. Here's a closer view of here's a closer view, and you can see some beds dipping here, and now you can tell, like this, you could imagine walking up to this area, looking at it, and you could measure this angle. And typically what I would do, I'd take my canteen or my water bottle, I literally would pour a little water on the rock. Water runs straight down due to gravity, so pretend this arrow would be the water dropping down here, and then I could lay my compass or my level app on my iPhone here, and it would tell me, these rocks are dipping 35 degrees into the earth. And then just doing simple geometry math, okay, if this is dipping 35 degrees, then how deep is this rock unit 1 mile out, 10 miles out, 100 miles out. The strike then, I just turn my iPhone in this direction so that I'm at 90 degrees. There's a square 90-degree right angle there. That tells me the strike, and I can record that with my compass on my iPhone. So just two apps that are in every iPhone, and I presume they're in every Android phone and Google phone or whatever you have. Most have these things. You can do this strike and dip. And we do this in the field. Here, these guys are using what's called a Brunton compass to do this, but now you can use just your iPhone. So here is exposed rock. They're looking at it. They can see there's a dip to it, so they're putting their little devices on it and measuring strike and dip. And then this little symbol, so there's a little T. And notice there's the top of the T, there's the point. And here they've written the 45. That gives them the person that's reading the map the idea that, okay, it's dipping at a 45-degree angle. We do this all over the place, such that, we can know the direction of dips. Now, anticlines and synclines are two-dimensional features, but what about in 3 dimensions? The Earth actually gets pushed up and pushed down by plate tectonics, and it creates 3-dimensional features. Domes are merely 3-dimensional anticlines. So look, here's a giant area. Let's say this is 250 miles across. 250 miles across in either direction, so huge. In the subsurface, these slices in the Earth, you see the big anticlines, but then they get sort of weathered off and cut off at the top, and it creates this sort of bullseye shape that we call a dome. Notice also they've marked the oldest strata up here in the middle and the youngest at the edges. So the next slide is the same thing, but larger. So here is the picture of the dome enlarged so you can see it better. And again, you notice that they have the huge syncline features if you just look at it in 2 dimension, the slice through the Earth. But 3-dimensionally, it creates this large dome. And then look at you can see a few of them here. I'll circle with the cursor. There's one of those little strike and dip things. Notice the dips are all pointing away from the center. That's because something has pushed this up in the center. The rocks dip away in every possible direction. How do we know that? People like these young geology students and professional geologists and geologists that work for geological surveys and classes go there and measure these things and then record it and put it on maps. The rock types are shown by different colors on the maps, and we know that this is the structure that exists. So something in this area pushed it up. If you erode off the top, it cuts it off, and then what happens is the central part is oldest and the youngest is at the side. So this is very important to know. A dome is just a 3-dimensional anticline surface. How you know it is that the dips are all going to point away from the center, and the center is going to have the oldest rocks, and they're going to get progressively younger and younger and younger to the edges. If you have a basin, then you have the opposite, if you have a dome, you have the opposite, which is a basin. Basins are merely 3-dimensional synclines, places where the Earth has been pushed downwards. Notice if you're just looking at the rock types, let's just say you're flying over them with an airplane, you'd see another bullseye structure. You wouldn't know, is this a dome or a basin? But if you go there and look at it, you would see that the dip symbols all point in the direction of the center. So here the dips are all pointing towards the center. That tells you that they're dipping to the center. This is a syncline. In synclines, it's the exact opposite. The youngest strata, the youngest rocks are in the center, and they get progressively older and older the farther you go out. So on the exam, expect to see some picture of a dome or a basin, and then I can ask you the direction of the dip symbols, or you'll see a picture with dip symbols. Is it a dome or a basin? Where do you find the oldest strata? Where do you find the youngest strata? Is this an example of a anticlinal structure or a synclinal structure? All of these things are possible. I'm going to end this part of the geologic mapping and continue this particular lecture as a second narrated lecture on our local geology and local geologic maps.